Hey everyone. So we are all ML engineers from Pinterest, and we've been using Ray for a few years. Today we're going to talk about how Ray has been a big breakthrough for ML productivity for our stack. So before we get into that, I just want to give a primer. As you all know, Pinterest is a social media app. We compete in the attention economy. Basically, we're competing with Snapchat, like TikTok, essentially to get more and more user engagement. And it ends up being a function of few things. One is our resources, how much GPUs we have, how many models we can train. The other is what techniques are we using? Are we using the state-of-the-art, like best in the class recommendation system techniques? And the third, often ignored factor is, what is our time to build and iterate? What is our idea to iteration velocity? And that ends up being playing a very interesting role. So a case study like the red circle, if you see on the other diagram. So sometime at the end of 2023, we shipped a new technique which was very good for our engagement. We gained a large percentage of time spent after shipping that. But early next year, Snap also built the same technique. And the big gains that we got in engagement, we immediately lost. So why invest in ML productivity? Because attention economy essentially is an arms race. So everybody's competing to get the next bigger, better model. So we not only need to come up with those techniques, we need to come up with them fast. What we've observed over the years is that ML data layer, like generation of the data set that cracks the neck-rexes technique, ends up being a bottleneck. So these are like few examples of common techniques that we use, adding a new sequence feature, exploring sampling strategies, coming up with future rewards. All these take a lot of time to just generate. So we have like long waiting times, either due to forward logging waiting or Spark jobs that take a lot of time to generate, and they're very costly as well. So following a Ray-based technique, we developed something we call fast ML stack, which brings down the time to generate these data sets or train models using these data set iterations blazingly fast. It's almost a paradigm shift for us. And these things are generated using two innovations. One is use of Ray heterogeneous clusters. Essentially what we did was we wrote Ray data workflows using map batches Ray UDS for most common use cases that we ran into. And then we replaced them with replaced forward logging and Spark workflows with Ray data workflows. The other was using intelligent partitioning. We standardize our stack to follow iceberg-based partitioning that we'll get into. Combination of these two techniques is responsible for the dev velocity breakthrough that we've observed. So let's get into both of these and what they mean. So I want to take the example of sampling and set motivation for difference between the batch and streaming paradigm. So batch paradigm is the old paradigm with Spark. So say once the unsampled data set gets available, we run a Spark job that selects, say on a positive to negative ratio. This job ends up taking some time to generate because we need to compare, because this is a big data job. And only after the final data set is materialized, the sample data set gets available. And that is when we can start training. So sampling iterations end up taking few days because we have to generate all of these different sampling ideas, and these jobs take a lot of time. Streaming paradigm is, however, slightly different. So once the unsampled data set is generated, we don't generate another sample data set that we materialize. We directly rewrite this sampling workflow as a Ray UDF, and we just use it at the time of training. So the training can begin right away. So trying any new sampling iteration takes from the time reduces from few days to few hours. And so this is not really a new ask. Our company has been trying to do this for a while, but Ray heterogeneous cluster totally unlocks it. So earlier when we tried moving sampling to just before training, like in the example on the left, we saw a lot of drop in throughput. So essentially, say using a single P4D machine, we would get bottlenecked on CPU workloads, putting arbitrarily complex sampling logic. But with Ray heterogeneous cluster, we have the ability to add more and more CPU nodes to maximize GPU utilization. And that unlocked, because of this, it unlocked arbitrarily complex workloads at the time of training. So all we did, like this was the hammer that we found, and then we found a bunch of nails. So we figured out all the data workloads that were causing us dev velocity delays, and we moved all of them to Ray. The other big unlock for us was stack standardization with what we call intelligent partitioning with Iceberg. So we added some user ID based bucketing. So we co-located data sets that belong to a particular user in the same bucket. What that allowed us to do is, across different tables, we are able to find where a particular user ID related role lies. And it creates a known pattern in the data. How does it help? It helps for one of the most common data operations, which are joins. So again, like we can compare like Spark versus batch workflows here. Imagine we need to perform a join, which is a very common operation for, say, like a feature backfill. We have a train table that has 1,000 columns and another feature, like a user feature that has, say, like 5 columns. In the Spark world, if we want to do a join, we need to compare all files to all files. And hence we do a Spark join, which creates a workflow which ultimately creates a 1,005 column and then writes this table. Only once this table is fully materialized can we start training. So this adds another delay. With Ray and Iceberg-based intelligent partitioning, we can do better. So we already know that when we do the join on user ID, we only need to join same user buckets with each other. And the way we have configured these buckets, we can load both of these buckets from table 1 and table 2 together in a Ray CPU cluster, and then just do the join as a part of CPU operation. This, like, because of this constraint, the wait time goes down significantly, and we don't even need to materialize the data set. So this is what unlocked fast feature backfills for us. So combining the two techniques, distributed data loading and fast feature backfills, we are able to transform a lot of our ML workloads. Samir and Philip today are going to dig deep into sampling and future reward exploration, which have been like the biggest, one of the biggest unlocks for our team.
Hey everyone, I'm Samir. I am a machine learning engineer on Pinterest's home feed ranking team. I'll be talking a little bit about how we utilize the paradigm that Kritarth introduced to improve and revamp the sampling infrastructure of Pinterest's home feed ranking. So first of all, why is sampling important? Rex's datasets are often very imbalanced, where we have a small number of positive examples and a large number of negatives, where a positive is essentially an item that appears on a user's feed that they explicitly interact with, let's say through a reaction, comment, download, anything like that. Whereas a negative is what we call an impression or a pure impression, which is something that appears on the feed but is not interacted with by the user, and they just scroll past it. Given the much larger quantity of such negative examples, we typically address it by downsampling negatives. But like, what is the best strategy to downsample negatives? Like, what should the downsampling ratio be? Should we perform some sort of post hoc weighting on the impressions that we finally sample? Should the sampling be random, or should it be smart in the sense, like, should we decide what fraction of hard and easy examples to sample? All of these are open questions, and they're independent levers that we can move around to get best engagement. But the problem is that iterating over such ideas is very difficult because this is different from, let's say, a pure modeling change where the data remains static, constant. In this case, every single change to any sampling parameter corresponds to a new dataset. Constructing which and managing which is difficult. So the previous slide talks about negative downsampling, but sampling also comes up in the case of managing positive examples. So the following is an example that I'll run with for the next few slides, and it's a real project that we worked on earlier this year. So for context, Pinterest's home feed ranking model is a multitask learning model which jointly optimizes for a bunch of user actions, such as saves, clicks, shares, etc. And earlier this year, we wanted to experiment with adding 2 new heads for new actions for downloads and screenshots. Now, generally, the way we do this is that whenever we add a new action to the model, we also change the sampling where we ensure that we are sampling all instances of the newly added action and including it in the training dataset. Now, this can also become slightly tedious, especially if, like in this case, we wanted to experiment with adding multiple actions simultaneously, and we were curious about what the impact would be on adding each of them independently and adding both of them together. So just in this case, what this means is that we wanted to train 4 models, like the blue boxes down here. One is the control model. One is a model where we just add the download head, one just for the screenshot head, and one for both the download and screenshot heads. Now, the issue here is that each of these models need their own datasets. One, the control dataset, one with just the all download examples included, one with all screenshot examples included, and one with examples from both those actions included. This has a bunch of disadvantages for us, as Kritarth already hinted initially. The biggest one is the number of days it takes to generate this dataset. It's like it could be up to a week for 4 datasets, and that's like a week spent before we can even start training a single model. Other than that, obviously, there is like we are generating and storing datasets which differ from each other slightly, and so there's associated S3 and compute costs. So the way we utilize Ray last mile processing is that we use the we transfer the exact same sampling logic, move it from these Spark jobs into the Ray trainer job itself, which essentially solves for all the problems that we initially had. So now, because we are able to specify sampling config along with the rest of the trainer config, it means that there is no delay for data generation now. It happens on the fly. We don't really have to do any batch processing jobs. Similarly, because we are not computing, we are computing data, and so there is some associated cost with it, but we are not storing, we are not persisting these sample data sets anymore, so there's some cost saving there. And we validate that with both these paradigms, with the batch processing and this Ray last mile streaming paradigm, we get the same model performance through an online AA test. Coming to the cost, so this table has our traditional batch sampling on the first row and in-trainer sampling in the second row. So we completely drop the cost of our batch compute jobs and storage cost for these datasets, moving to in-trainer sampling. And these are annual numbers. So for across a year, this is what we would have spent if we had been generating all these datasets. But the third column is training cost increase per model. Now, because we are moving some of this processing into the training job itself, there's a small increase in cost we incur because of that. So obviously, now there will be a threshold at which if we train more than X amount of models, the in-trainer sampling will start being more expensive. But because we use this paradigm only for model training, which varies the dataset, the number of such models we train is pretty small. So for us, it's less than 750 models trained with these alternative datasets, which ends up being a more than 350K per year cost saving. Next, one important limitation of this paradigm comes from observability. So now we are changing the sampling strategy. We're essentially changing the distribution of examples across our training dataset. And now, because all of it is happening within the training job, we don't really persist it anymore, and we can't query the training table anymore to see what our changes look like and what finally went into model training, which is quite a blind spot. So we have found a workaround. Like the way we have worked around this is that we log a couple of important columns during the on-the-fly sampling. So the important ones here are row IDs and the Boolean sampling mask, which tells us during the training job, which tells us what row we are using, like what finally got sampled and what got dropped. And then post hoc, we can join these columns using the row ID with the original unsampled data set and kind of recover the actual data that would have gone into training. Yeah, with that, other than the wins in dev velocity that I already talked about, this has unlocked a bunch of sampling related ideation. So as I mentioned in the very beginning, there are a bunch of orthogonal levers that we can move around to find the best sampling strategy to either drive engagement or reduce cost. We have been able to do both of those things because like these would just have been infeasible because of the amount of time it would have taken to generate these datasets, which that's not the case anymore. For example, for cost saving, it could be things like reducing the impression ratio and like trying to find ways where even though we reduce dataset size, we are able to get the same engagement. And we're also looking at getting engagement wins by data selection, so things like harder negative sampling. So where traditionally we just sample negatives randomly, we are looking at selecting examples which are difficult for the model to classify with the hope that that would allow us to learn better decision boundaries with the potential for engagement wins. That's about sampling. Philip will be talking about downstream rewards and how we apply Ray last mile for that, which is like a very Pinterest specific, unique, and interesting use case.
Awesome. Hey, everyone. So my name is Philip, and in the last segment, I'll talk about the in-trainer label aggregation. This was basically an effort that helped us drive down the time to online experiment with new labels from 6 weeks to 2 days, so huge dev velocity improvement. But before we get into that, let's just quickly run through some key terms that we used across Pinterest so that we are all aligned when we are talking about the examples. So the first thing is that when you open in Pinterest, you land at home feed. Home feed is the cursor, is the first surface, and we try to recommend things that you hopefully like. So for example, I like architecture, and there is a pin that caught my attention, so I would want to see more like this. So what I do is I perform an action that we call a close up. Once I close up on a pin, it takes me to a related pin surface. In this surface, you're served pins of a similar nature. And I really like the one that I highlighted in blue. This is a beautiful BRK Engels architecture. So I close up on that one as well, which brings me to a related pin surface for this pin. And I still like this pin the most, so I would want to keep it somehow. So an action I can perform is called repin, which allows me to store this pin in one of my curated boards. Board is just a collection of pins. So I already have a board for architecture, so let's just put it there. Bam, and it's in the board. So every time I visit this board, I can also interact with this pin. The final thing I want to mention is called, this is from an engineering point of view, we have this term for rabbit hole. Rabbit hole is basically the sequence of traversals that the user does across the related pin surface and the actions that they take there, and it has to originate from home feed. This brings us to the concept of downstream rewards. Downstream rewards are basically an effort to serve pins on a home feed that promotes this long-term behavior that drives the users into these rabbit holes. And so as was previously mentioned, we are from the home feed ranking team. So what we control is really what we serve on a home feed. But what we want to achieve with what we serve on a home feed is this. We want to drive the users into these rabbit holes. We want them to perform as many positive actions as possible, including clicks, other repins, shares, and stuff like that. But you can immediately see why this is difficult. This is difficult because it's not the next immediate action modeling that you usually do when you model it on your own surface. Like on home feed, you would model for immediate repins. This is happening somewhere in the future. So there is a sequence of actions that the user takes after the initial pin recommendations. And you have to attribute it back correctly to create a label, and you have to model it well. So this creates a lot of challenges. So how are we actually modeling this? Well, we model this with specialized sets in our ranking model. We, for example, have a head for downstream repins. We have a head for downstream clicks or board visitations. The challenge here is that because this is a supervised paradigm, we require labels for this, and labels are really crux of this because calculating labels for these forward-looking actions is really difficult. there are multiple challenges, not just the forward-looking nature, but also the nature of these downstream rewards themselves. You can optimize for variety of actions, for combinations of actions, and because this is working with sequences and the actions are happening in the future, you can also work with discounting factors. So ideally, you would want to be able to run some hyperparameter search over, say, the discounting factors. The most important challenge here that Kritar has already spoken about is that we were calculating these labels in a Spark-based workflows. And this is really difficult because every time you want to experiment with a new label, you're introducing added cost, you have to modify the production workflow, and most importantly, you have to wait for the data to forward lock, which takes a lot of time. It used to take multiple weeks. So I just wanted to show this simplified figure where assume we log all impressions across the Pinterest surfaces. From that, we derive our training data for the home feed ranker. But we also had to do this repeated self-join, which is then fed into the DR label aggregation job to derive a subset of these downstream rewards reprints that are then joined back onto the training data using impression ID. And we really wanted to get rid of this because this is difficult to maintain, it's expensive, and it's slow. So what did we do? Well, we made a foundational shift to sequence-based data, and we introduced something we call DRV2. DRV2 captures user single-day actions into sequential data. So an example, we know that actions are the strongest and least noisy signals on the platform. So let's look at an example. Here, within a single session, the pinner performs some activities like scrolling, returns, and other stuff, but there's several highlighted actions that we care about, like the close-ups, clicks, and repins. So what we do every day is for each user, we capture a set of these sequences like pin ID sequence, surfaces traversed, action sequences that are all aligned under the same index. And we capture these key actions in them. So you can see how we capture the close-ups, the clicks, and repins. And this is, I repeat, these are sequences. And the beautiful thing about these sequences is that actually, if you use various combinations of these sequences, you can derive any downstream label that you want. So let's look at an example. Well, let's try to derive DR shopping long click label. This definition of the label is a bit convoluted. It requires that the user is in a rabbit hole. They click out from Pinterest for more than 45 seconds, and this click out happens on a shopping click. So if you were doing in the Spark, this would be a bit tricky to replicate. Well, let's derive the label now. For a single training example, we first need to determine what is our position within the single day sequences, because as I mentioned, the sequences capture the full day. So we first use pin ID and request ID to locate the user within the sequences. We can see that he's there at the user at the index 100. Next, we use the surface sequence to determine where the rabbit holes are happening. After that, we can use the supplementary sequences like the action sequence to determine where clicks happened, and action duration sequence to determine the duration of these clicks, as well as the pin type sequence to determine what type of pins these clicks happened on. And you can immediately see that you can kind of think about this in terms of like Boolean masking paradigm. And if you just take an intersection of these masks, if you get an example that meets all the conditions, you can actually derive the label. So you can derive these labels in a vectorized fashion using these sequences. And this is really beautiful. It's also beautiful for implementation. So what we did after is we basically moved away from the Spark job that was doing these self-joins with the logged impressions, and we replaced it completely with just joining the DRV2 sequences based on user ID onto our training data. Well, a question you may ask now is, what does this all mean? You used to have labels in your training data, now you just have sequences. The models clearly don't work in these sequences, so what do you do? Well, this is the point where Ray comes in. Using Ray, we constructed something we called last mile label aggregation framework. And this is a very robust but simple framework that allows the user to derive any downstream rewards label within a single line of code. How it works is basically that from Iceberg, we read the training data that includes the DRV2 sequences. Then we funnel this through multiple user-defined functions in the Ray data loader, which finally drops the DRV2 sequences and replaces them with the labels that were derived. The label derivations are actually based on the vectorized operations in a similar fashion like I showed in the example. We tried to optimize this as much as possible, and we actually achieved net zero training cost by using a lot of vectorization, obviously, and then some code compilation. The impact of this was quite high. As I mentioned at the beginning of the talk, we were able to drive down the time to online experiment from 6 weeks to 2 days. And so an illustration of this is initially when I was first working on downstream rewards, when we started working on a new idea, it took multiple weeks. The model could have changed before we even got to the MVP. These days, when I go to work on Monday, I get an idea, I can have a model online on Tuesday and first read on the model performance by Friday, which is an amazing dev velocity improvement. Furthermore, I can run multiple versions of these labels like this very easily, because this is all parameterized in Ray and it's derived on the fly. But we didn't stop there. We are trying to push for more challenges. So basically, as I mentioned at the beginning, we have this board revisitation behavior where users repin a pin, and then they revisit it in the board. Well, the challenge here is that this is even more forward-looking operation than most of the downstream rewards. This is because our data science team has determined that the average time to revisit a pin is usually 2 to 3 days. This means that it requires multiple days of the DRV2 sequences to be ideally used for the label derivation so that we get like a representative performance. Again, extremely difficult in Spark. We would first have to merge the DRV2 sequences and then join them onto the training data, which would blow up our workflow cost and storage costs as well. Well, we solved this problem by using our full array stack. We were able to introduce the multi-day board revision label into production by basically first taking unsampled training data, using the in-trainer bucket join that Ritar has talked about, to join multiple days of the DRV2 sequences onto the training data on the fly during data loading. Then we push this through the last mile label aggregation framework to derive all the downstream rewards labels that we wanted, including the multi-day labels for the board revisitations. And finally, using Samir's in-trainer sampling, we created a training data set with the composition that we wanted. So this was something that we were previously unable to do. Once we introduced all our array tools, we were able to ship this into production. So in summary, I would say the two key things are that using the array tools, we were able to supercharge our developer velocity, and we were also able to start optimizing business objectives that were previously impossible, even though very important, like the multi-day board revisitations. Last but not least, while it was three of us presenting these efforts, it's a team effort. There are many colleagues at Pinterest that worked with us effortlessly to make this happen. We appreciate all the help and all the great ideas, so I wanted to mention them. And this is it from us. Thank you so much for your attention.
I think if there are questions, we can take a couple of questions. Okay. He raised his hand first.
Yeah, thanks for the talk. This is very interesting outcome. I'm very curious about the effort you folks took to migrate all the Spark compute job, for example, the downsampling job, to Ray, and frictions. Anything learning from there you're willing to share? Yeah.
I think this is a very interesting point. So one of the reasons we wanted to move our workloads to Ray was because ML engineers are very familiar with Python and not as familiar with PySpark. So writing these UDFs in regular Python and like pandas was kind of more intuitive as well. So yeah, I think like the way we generally did, I think Samir mentioned it at some point, we run AA experiments. So we have these Spark workflows, and then we just quickly came up with like a panda-based UDF, and then we just did a performance, like you trained a model to see if the performance was neutral.
Just have time for one more question. And then you can catch the guys in hallway because we need to empty the room for the next talk. So one more question.
First of all, thank you for the really interesting talk. It was quite technical, I would say. So one of the bottom lines of your talk that I understood was basically we shifted from the batch paradigm with all the backfills and all the stuff towards more streaming-like paradigm when all the CPU computations are performed on demand closer to the actual training, for example, or on demand. And my question was, like, even before Ray, there were various infrastructural components, technologies like Spark streaming or Flink or other approaches how to do things in stream-like paradigm on the fly, and also some shift from the batch paradigm. Did you try to evaluate them before trying to go for array? And did you have any other attempts before?
So I'm not super familiar with those paradigms if they also worked with training on the fly. Yeah, I think we started exploring this mainly with the sampling problem and doing this on the fly with training. So yeah, we did not explore those that much.
Okay, thank you.
Thank you, Philip, Samir, and Kritarth.